Let's say Stella begins infall into a 20 million solar mass black hole from r0 equals 10 gm, and Tom watches her from that same distance of r0 equals 10 gm, using a jetpack to keep him at that distance. Worrying about her crossing the r equals 2 gm barrier, which is the so-called event horizon of the black hole, Tom decides to catch up to Stella before she reaches it. Luckily, Tom's jetpack enables him to travel at near light speed relative to the black hole. How long can he afford to wait before beginning his rescue? That is the question we will answer in this video. We've already drawn out Stella's space-time trajectory in purple, using the equation for infall developed in the last video. But to determine how long Tom can afford to wait before beginning his rescue, we need to determine the trajectory of his rescue. We begin with the Schwarzschild metric for radial motion with the azimuthal component set to 0, since Tom will only be traveling radially inwards to rescue Stella. Let's assume Tom performs the rescue at the speed of light, which is an upper limit to what is possible according to the laws of physics. In that case, we know that in flat space, when r approaches infinity, dr by dt is equal to 1, reminding us that the space-time interval for light is equal to 0. Okay, let's now solve this equation for dt. Here we have chosen the minus sign in front of the dt because we are talking about radial infall. This integral is not difficult to solve. Let's make the substitution that u equals 1 minus 2 gm over r. Then du equals 2 gm over r squared dr. Notice that 1 minus u equals 2 gm over r, so 1 minus u squared equals 2 gm squared over r squared. And therefore, 1 minus u squared over 2 gm equals 2 gm over r squared. So we can make this substitution back into our expression for du. Now let's solve for dr and then substitute everything back into the original integral. Okay, we can solve this integral by the method of partial fractions. Let 1 over u times 1 minus u squared equal a over u plus b over 1 minus u plus c over 1 minus u squared, where a, b, and c are constants. To find these constants, we first multiply through by the entire denominator. This equation must hold for all values of u. So letting u equal 1, we can immediately see that c equals 1. Letting u equal 0 lets us see immediately that a equals 1. Finally, letting u equal 2 and substituting in the values for a and c allows us to see that b must also equal 1. So now let's substitute this partial fraction decomposition back into the original integral. This equation is easily integrated by inspection. The left-hand side is just negative t. The first term on the right is ln u. The second term on the right is negative ln 1 minus u. And the last term on the right is just 1 over 1 minus u. And let's not forget the constant of integration at the end. Now let's substitute back in what u equals in terms of the Schwarzschild radius r. Let's clean things up a little bit. Now let's find out the constant of integration by setting t equal to 0 when r equals the original position r0. Let's substitute this back into the original equation for Tom's time. This is the final expression for Tom's trajectory. Let's plot it in green on the graph. As you can see, at the speed of light, Tom is much faster than Stella, but he slows down to a halt at r equals 2 gm just like Stella does. Instead of leaving right away, remember that Tom waits for a bit before deciding to rescue Stella. Notice that as Tom waits longer and longer, the point of intersection between the purple and green paths gets closer and closer to r equals 2 gm. The point of intersection is where Tom catches up to Stella in space-time, and it gets closer and closer to the horizon the longer Tom waits. Since it takes Stella an infinite amount of time to cross the horizon, can Tom wait forever? We can answer this question mathematically by setting Tom and Stella's time equations to be equal, and then we solve for Tom's wait time. This equation would be good enough to find out Tom's wait time to intercept Stella at any r value, simply by plugging that value into the equation for a given r naught. The only r value that may give us some trouble is r equals 2 gm, since the logarithm argument will then be 0 divided by 0. So let's simplify the logarithm argument by multiplying the numerator and denominator by the denominator's conjugate binomial. Now let's multiply top and bottom by r over r naught. As you can see, the r over 2 gm minus 1's cancel on top and bottom, and we are left with our final expression for how long Tom can wait before being able to catch up with Stella if he travels at light speed with his super-duper jetpack. How long until it is impossible to catch Stella before she crosses the r equals 2 gm barrier? We simply substitute in r equals 2 gm and the original position of r naught equals 10 gm into our waiting time equation. And now let's simplify a little bit. This results in a grand total of about 30.55 gm. So let's back up Tom and see how the blue intersection point of Tom and Stella's path through space-time behaves. As you can see, Tom intercepts Stella well before the event horizon, in a time well below the top of the graph, until about 30 gm, at which point the blue intersection point flies off the graph and Tom intercepts Stella at the event horizon at t equals infinity, since it takes infinite Schwarzschild time for anybody to reach the event horizon, including Tom and Stella. If Tom waits longer than about 30 gm before flying off at the speed of light to intercept Stella, he will meet her after they both cross the event horizon, when Schwarzschild time is no more. But at least they will meet inside the event horizon and reunite once more. That is, unless Tom waits longer still, and instead they meet at the singularity. How much longer would Tom have to wait for that, you ask? Well, we just need to back up our wait time equation and sub in r equals 0 rather than r equals 2 gm. When we set r equal to 0 in the inverse tan term, the argument becomes infinity, and the inverse tan of infinity is pi by 2. In the next term, we can write r as root r times root r, and we bring 1 root r into the second square root. Then, setting r equal to 0 in this term, we see that the term vanishes. Setting r equal to 0 in the next term yields negative 10 gm. And to see what the argument of the logarithm equals in the limit as r approaches 0, let's put the r that's outside the squared brackets inside the squared brackets, which therefore turns into a root r. The first root r can be brought inside the large square root sign, and we can see that as r approaches 0, the numerator approaches 1, and the denominator, of course, is equal to 4. Adding this all up together yields a grand total of 31.21 GM. So Tom is only able to wait 0.66 GM longer than the horizon wait time, before he cannot even rendezvous with Stella, before she reaches the singularity inside the horizon. Here are the equivalent times corresponding to a 20 million solar mass black hole. So if Tom waits more than 50 minutes or so before executing his high-speed rescue of Stella, he will only catch up with her after she crosses the event horizon, even though it takes infinite Schwarzschild time for her to cross. Thank you for watching.